So today I'm going to be talking about work that I've been doing with my advisor, Jim Gielen, and what we've looked at is the extremal function for linearly dense minor closed classes of matroids with bounded branch width. So here we're going to have an example of an extremal function on a minor closed class. And what is an extremal function? What we do is we input what we want a rank of a matroid to be, and what is outputted is the maximum size of a simple rank n matroid in our class. So here what we have is the class of graphic matroids, which have no k33 minor, and we know that the extremal function is given by 3n minus 2 when n is equivalent to 2 mod 3, and equality is attained by taking two sums of copies of k5, and then the extremal function values to 3n minus 3 otherwise, and then equality is attained in this case for planar triangulations. So we have a couple nice things that we can see in the extremal function of this class. The first of which is that it tells us that this class is linearly dense. And what does that mean? So that means that we have a constant c such that any matroid in our class has size bounded above by c times the rank of that matroid. And so in this class, what we can see is the constant c is 3. And we want to look at that a little more specifically. So what we're going to look at is what's called the limiting density of the class. And what that is the lim sup of the density of extremal members of our class as the rank goes to infinity. So we can see that the limiting density is exactly 3 in this class. And we have one more nice observation to make about the class, is the extremal function exhibits a periodic behavior. So what does that mean? It means when we're evaluating the number of points in our matroid, we can say, okay, it's equal to the limiting density of the class times the rank of the matroid, and then we perturb by some number of elements, and the number of elements is periodic. So we see here a period would be 2, 3, 3, 2, 3, 3. And so this leads us to our main theorem. And our main theorem says that if we have a minor closed class of matroids, and that class is both linearly dense and has bounded branch width, then first what we can do is we can show that the limiting density of the class is rational. And then what we can show is that the class has an extremal function which exhibits this periodic behavior that we saw. Now this was proved for such classes which are representable over a finite field by Capadia, and that proof is really nice. It's got a lot of great ideas going on, but it uses something that we're not allowed to use. And that's a theorem by Gielen, Gerards, and Whittle, which says that matroids which have bounded branch width and are representable over a fixed finite field are well-quasi-ordered under the minor relation. So we know that we can't use this because already we have the class of matroids which have rank at most 3 being not well-quasi-ordered under the minor relation. So what do we do to get around this? Well, what we do is we introduce a new well-quasi-order. And this is really, really nice. So what we're able to do is we're able to say, give me a collection of simple matroids which have bounded branch width. Then what I can do is I can find one matroid in this collection which has a minor which with size and rank exactly equal to the size and rank of another element of another matroid in this collection. So we also conjecture that this is true for just matroids, simple matroids in general. And so you might ask, how does this well-quasi-order help us to see that we have this periodic behavior exhibited in extremal functions of our class? And to tell you that, first I need to introduce what the main structure we use is. And the main structure that we use is called a K-dissection. That was touched on yesterday by Cynthia in her talk. And what it is it's an ordered partition of our ground set of a matroid, which gives us a sequence of nested separations of our matroid. So here, the ordered partition of the ground set is S1 up to S5. And then what we can see is these vertical ovals correspond to the boundaries of the separations. And specifically, say we look at the shaded oval, that corresponds to the boundary of the separation given by S1 union S2 and S3 union S4 union S5. So having these dissections is really nice for helping us find the density of a matroid. Because what we can do is we can say, okay, I can't really figure out maybe what the matroid looks really quickly, so what I can do is I can figure out what each of these individual parts looks like, and then what is the size of the matroid as a whole? It's, if the matroid is simple, of course, you just take the sum of the elements in each part of your dissection. And then what's the rank of the matroid? You take the sum of the ranks of each part. And then you have to remove the ranks of the boundaries. So one thing that we were able to show is we used a result of Gielen and Ben David to tell us that large matroids give us long K dissections. And how do we use this to find our periodic behavior in our class? So what we do is we take a handful of matroids, an infinite set of matroids, which attain extremal values of our class. And what we do is we look at long dissections given by these matroids. So what we say is, since we have infinitely many extremal values of our class being attained, we're going to have our matroids being arbitrarily large. We can find arbitrarily long dissections. And so we can find a handful of dissections that look like, that are getting longer and longer. And right now, we don't really know what the dissections look like in full. But what we can do is we can use techniques given by the paper of Rohan, along with our well-quasi-order, to say what we can do is find minors of these dissections which look something like this. We can describe them entirely by a triple ABC, where A, B, and C are matroids. So a triple ABC is going to be a class of dissections where the first part of our dissection looks like the matroid A, the last part of the dissection looks like the matroid C, and then everything in the middle looks like B. And so we can see that this has a periodic looking behavior in terms of density, because if you wanted to build up from the ground, you know the density of your first dissection, and then when you add in a new part B, you're going to be adding a handful of points, you're going to be adding a marginal amount of rank, and then you add in B again, and through this iterative process, each time you're increasing by the same number of points and increasing by the same rank, so you can see where this periodic behavior comes from. So to recap, what we did is we took an infinite collection of matroids in our class, which cover distinct extremal values of our class. And somehow we get this triple, which covers infinitely many of those matroids. Now, we had to be pretty careful here, because what we wanted to do is make sure when taking minors, you have to go from one extremal matroid to another extremal matroid, or otherwise you run into problems. So there's some tricky stuff going on, but this is really nice. So in total then, what we can say is we have an infinite collection of triples, A, B, C, which cover all but finitely many of the extremal values of our class. And then the last little touch is what we do is we take this well-quasi-order that we have, and we tweak it a little bit to make it work for dissections as well. And so then we have these dissections are well-quasi-ordered. And so we have that the triples are well-quasi-ordered also. And so then what we get is finitely many of these triples cover all but finitely many of the extremal values of our class. And so now you can see where the periodic behavior comes from in our extremal function. What we have is finitely many triples. Each triple seems to have this periodic behavior. You know, putting them together, it's going to end up with something periodic. So this is nice, but we're not quite done. And I say that somewhat in jest, because this is how the proof goes. However, what Jim really wanted, Jim, Gerards, and Whittle, what they wanted was to show this for all linearly dense minor closed classes of matroids. But we only showed it for linearly dense minor closed classes with bounded branch width. So that's some food for thought, and thank you for your time.
Are there any questions for Owen?
Can you say something about the length of the period as a function of the branch width, or even also the delta denominator?
Okay, so the length of the period, it comes into play. What you look at is, with this well-quasi-order, really we're going to define it on rooted matroids in our class. And then when we're going to look at the minimal elements in these rooted matroids, which we can think of as then you plug together these rooted matroids to get these dissections, it's going to be a function on the product of the ranks of those. So when you're taking your well-quasi-order, you're going to have interior elements which are all going to be minimal. And so you can see how then when you're perturbing the rank by that amount each time, that's how your period's going to come.